This is supposed to be a workshop, so I would appreciate it if you could keep it as such. That is to say, please feel free to interrupt me if you have questions. Nevertheless, let me go over the 4 basic parts of the workshop. In the first part, we shall emphasize that the Black-Scholes model is just a black box, so we call that the Black-Scholes black box. In the second part of the presentation, we will look at the world as if it were deterministic. We would look at the world as if it were deterministic, and in that context, how would an option pricing formula look like? In the third part, we will relax the assumption of a deterministic world and will assume that the world is probabilistic or stochastic, whatever term you are more comfortable with using. And we shall adjust the deterministic formula to fit a stochastic world. Finally, we can talk about the extensions of the Black-Scholes formula. That is to say, the original Black-Scholes formula was derived for non-dividend paying stocks, for calls and put options on non-dividend paying stocks. Needless to say, we are a bank, and for a bank actually to talk about options on non-dividend paying stocks may not be that much meaningful. We are more in the business of selling either explicit or implicit option products on foreign exchange, interest rates, and so forth. The Black-Scholes formula can be used with some modifications for other instruments such as interest rates, foreign currency, commodities, and so forth. This is not necessarily always correct, but in the fourth part of the presentation, we can talk about how the Black-Scholes formula can be extended for instruments other than non-dividend paying stocks. Furthermore, if you have questions about the Cox-Ross-Rubenstein model, delta hedging, and so forth, I would urge you to bring them up in this last part of the presentation. So this will be the general outline of the presentation. What I will be following more or less closely is the write-up that you have in front of you called the Basic Principles of the Black-Scholes Option Pricing Model. There are some outlines that I've put together. So before I go on, are there any questions? Okay, then we can proceed with the first part of the workshop, that is to say, looking at the Black-Scholes model as if it were a black box. This Black-Scholes model is in the middle. It is the black box. That is to say, there are inputs that go into the Black-Scholes model, and there will be outputs that will come out of the black box. Okay? You can think of this as your amplifier. All right? Into the amplifier goes the output of the record player or the CD player or the FM tuner, and out comes a signal that will drive the loudspeakers. You can think of the Black-Scholes model in that context. Now, what are the inputs that go into the Black-Scholes model? Maybe you can refresh my memory. So let me try and take some class participation if you're so willing, please. What are the inputs that go into the Black-Scholes model?
The market price of the underlying stock.
The market price of the underlying stock, and we shall use some notation here, so it's best to get away with it right away, and that is denoted as S. That is the market price of the underlying stock. When we are dealing with foreign exchange or commodities and so forth, it will translate to the market price of the underlying security. So in a general sense, S stands for the market price of the underlying security, which is one of the inputs that goes into the Black-Scholes model. What are the other inputs that go into the Black-Scholes model?
Time to expiration.
Time to expiration, time to maturity, and that would denote by little t. In some formulae, it will be denoted as big T, but never big T or little t. That's usually the letters that are assigned to time to expiration. What are the other inputs that go into the Black-Scholes model?
Volatility?
Volatility. And volatility is denoted by the letter sigma. By the Greek letter sigma, it stands for volatility. Let me first finish all the inputs, and then I'll go back and talk a little bit more about volatility intuitively. What are the other inputs that go into the Black-Scholes model? The strike price, which is usually denoted by either X or K. In the notation that I've given out, I've denoted it with K. But you should be aware that if you're looking into the literature, in various books, various papers, and so forth, it can be interchangeably denoted as K, X, and I just realized sometimes even E. What else? What are the other inputs that go into the Black-Scholes model? One,
The discount rate?
the discount rate, or let's call it the risk-free rate of interest. Let's call it the risk-free rate of interest, little r. Again, depending on which book you're using, R will be defined to be either the risk-free rate of interest or 1 plus the risk-free rate of interest. In the handout that I have given, I use R as 1 plus the risk-free rate of interest, and that's also how the graphs drawn. Now, if you're talking about foreign exchange, for instance, an additional input that will have to go into here will be the foreign rate of interest. If we're talking about options on futures, then instead of S, we would have to have the futures price. If we're talking about options on commodities, we might have to have a term here that reflects the holding cost of the commodity, the carrying cost of the commodity. And what is the output of the Black-Scholes model? The output of the Black-Scholes model will be the price of the option, which is denoted as big C if it's a call option, or it will be denoted as P if it is a put option. Now, volatility is one of the most important inputs that goes into the model, if not the most important input. Everything else, the underlying strike price, the time to maturity, the exercise price, and the risk-free rate of interest can be readily obtained from just looking at market variables. Volatility has to be computed, and usually people have a hard time understanding what volatility is. Volatility is the standard deviation of the rate of change of the security price, whether it is stock or the interest rate or the or gold prices or whatever instrument you're looking at. It's the standard deviation of the rate of change. And it is in a way a quantification of our ignorance about how these prices move. Let me give you an example. What is standard deviation? Statistically, standard deviation is a term that is used in statistics, but what is statistics? Statistics is really a quantification of ignorance. When you do not know what's going on around you, you try to quantify it with such statistics as mean, standard deviation, kurtosis, skewness, and whatnot. Well, standard deviation is one of them. Okay, what does standard deviation mean? Suppose the mean height of the population of the world is 5'8", shall we say, 5'8" inches. Let us say that is the mean of the height of the world population. Now, if world population follows what is called a normal distribution function, okay, we have the mean 5'8" inches. And if the world population follows in height a normal distribution function, let us say that the standard deviation of this height is 2 inches. Okay? 2 inches. Now, what does that mean? About 66% of the world population will be within which heights? Anybody? Okay. That means that 66% of the world population will be between 5'6" and 5'10", right? And 95% of the world population will be within plus or minus 2 standard deviations of the mean, right? And what is that? That is 5'4" and 5'12". Okay. Now, similarly, the same is true for security prices. Now, let us assume that the mean DM dollar exchange rate, for instance, is 2 DM to the dollar. 2 DM to the dollar. Now, let us say that the volatility, sigma, and that is what our options traders on the 35th floor will quote you. Let us say the sigma on the DM dollar 1 year out is 10%. Okay? So what is 10% of 2 DM to the dollar? Well, that is 20 pfennigs, right? So that means that if 1 year options, 1 year Deutsche Mark options are selling at 10% volatility, that means that there's a 95%, we have 95% confidence that the Deutsche Mark dollar rate will be within 2 DM to the dollar plus or minus 20% of that 1 year out. Okay? So what is 20% of 2? That is 40 pfennigs, right? So that means that given a sigma of 10%, we expect the DM dollar rate, we have 95% confidence that the DM dollar rate will be between 1.60 DM to the dollar and 2.40 DM to the dollar 1 year out. That is what sigma is, intuitively. Again, if we look at our black box, the inputs are the underlying security price, the time to maturity, the volatility, sigma, the standard deviation, whatever you call it, the exercise price, the risk-free rate of interest, and the output is the call or the put price, depending on which model you look at. Now, this Black-Scholes model can be used in reverse as well. That is to say, you can put as one of the inputs either the call price or the put price. And then when you do that, what comes out? That is to say, in your black box, you can have this underlying security price, the strike price, the interest rate, the call price, the time to maturity, and then if you do that, what will be the output then? The output will be volatility, and that's usually called implied volatility. That's sigma implied. Now, I really don't know how the world started, but we can think as if the world started in the following way. And I think that will provide some insights into the workings of the model. Say you were the first options trader in this world. You know, on the 8th day, there were options traders or whatever. You took your Black-Scholes option pricing model and you put all your inputs, and out you got a price, a call price or a put price. Then you looked at that price and it looked to you to be very low. You didn't like it because it wasn't in synchrony with market prices, so to speak. And then you jacked it up. You said this is a better price given market conditions. You jacked it up. You might have jacked it up because this Black-Scholes model is not an accurate description of reality. The world does not have to follow a log normal distribution, or percentage changes do not have to follow a normal probability density function. The tails might be fat. There might be early exercise. And if you're just taking care of that with a Black-Scholes model, that is not entirely correct. You have to use the so-called Cox-Ross-Rubinstein model for American options. For one reason or the other, the Black-Scholes way of depicting the world might not be the correct way. And therefore, you might not like the price that you get out of the Black-Scholes option pricing model. You look around and you jack up your price. Okay? You do that, and then you say, okay, now it is very difficult to compare different options instruments. You know, they'll have different times to maturity, different exercise prices, and it's very difficult to compare them with just one number. But nevertheless, people are interested in